Ladies, this is lesson 7.6, and in this lesson we're working with exponential and logarithmic equations. So we're going to rewrite logarithmic equations to look like exponential equations and look at some properties of those, and then vice versa, exponential equations as logarithmic equations, and also look at some of those properties. So a couple vocab terms that you have are exponential equations, and those are equations where variable expressions occur as exponents. So instead of just having one variable in the exponent, you have an entire variable expression. And secondly, we have logarithmic equations, and these are equations involving logarithms of variable expressions. All right, so let's look at this first key concept, and you should see this on your note sheet. But this is the property of equality for exponential equations. So again, if b is a positive number that's not equal to 1, then b to some power, if b to some power is equal to b to some other power, that's going to be true if and only if those two powers are equal. So for example, 3 to the x power, if that is equal to 3 to the 5th power, then x equals 5. So 3 to the x power equals 3 to the 5th power. So let's look at an example for this. So here we have 6 to the x. Here's our example, the first one, and you should see this on your note sheet. We have 64 to the x power is equal to 16 to the x plus 1 power. Now, using this property, we have to have the same base. So 64 and 16 are not the same base, so we need to rewrite them with a common base. So if we rewrite 64 with a base 4, that's 4 to the 3rd power, all to the x power, is equal to rewriting 16 with a base 4 is 4 squared, all to the x plus 1 power. So if we rewrite 4 to the 3rd to the x power using our properties of exponents, we have 4 to the 3x power, and that's equal to, again, using our properties of exponents, we're distributing that x plus 1 to the 2nd power. So we have 4 to the 2x plus 2 power. Now, since we have the same base, both of these have base 4, we know that our exponents are equal based on that property of equality for exponential equations. So now we know that 3x is equal to 2x plus 2. So now we're solving for x. So we're going to subtract 2x from both sides, and we're left with x equals 2. So now let's just double check that this works. So you have 64 to the x power, which we said x was 2, and that's equal to 16 to the x plus 1 power, or to the 2 plus 1 power. So 64 squared equals 16 cubed. 64 squared, if you put that in your calculator, you get 4,096, and 16 cubed, if you put that in your calculator, you have 4,096, and those two are equal. So our x value, we can confirm, is equal to 2. In this second example, you have to remember the properties of inverse of logarithms, because here, in order to solve for x is in our exponent here, so in order to solve for x, we need to take the logarithm of both sides, and specifically, we're going to take the log of base 6 of both sides, because log of base 6 of 6 to the x power is just equal to x. So if we take log of base 6 of both sides, we have log base 6 of 6 to the x power is equal to log base 6 of 27. And again, using our properties, our inverse property of exponents, that log base 6 of 6 cancels out and is just equal to x. So we're left with x equals log base 6 of 27. Now we can't evaluate this because it's 27. 6 to some perfect integer does not equal 27, so it's going to be a rounded answer. So we're going to use the change of base formula to estimate this answer. So using the change of base formula, we have x equals the log of 27 over the log of 6, which now you can put this into your calculator. You can either use the common log or the natural log. Either one will work the same. And we get approximately 1.839. All right, let's look at another one where we're taking the logarithm of both sides. But in this example, we have a base e. But before we take the logarithm of both sides, we need to isolate that e to the some power. We need to isolate that exponential portion of our equation. So the first thing that we're going to do is subtract 8 from both sides. So we end up with 6 times e to the 0.25x power equals 12. The second thing we're going to do is still we want to isolate that e to the 0.25x power. So we're going to divide both sides by 6. And we have e to the 0.25x power is equal to 2. Now we can take the log of both sides, the natural log of both sides, because the natural log has a base e. So the natural log with base e of e, that all cancels out, and we're left with 0.25x equals the natural log of 2. Now the natural log, we have a button for that on our calculator, so we can just use our calculator to solve this. But we end up with, we need to divide both sides by 0.25 or multiply both sides by 4. You'll get the same answer either way. So our x value is equal to the natural log of 2 divided by 0.25, which is the same as 4 times the natural log of 2. So again, you can put that into your calculator using the natural log button. And x is approximately equal to 2.773. All right, try a couple of these on your own. You can pause the video while you work and then unpause for the solution. So to start off, the first thing you should do is recognize that 9 is the same as 3 squared. So rewrite 9 as 3 squared, and then take log of base 3 of both sides. So you end up with log of base 3 of 3 to the 7x minus 3 power is equal to log of base 3 of 3 squared to the 2x power. Then you can use your inverse properties, where that log base 3 of 3 on both sides cancels out, so you're left with 7x minus 3 is equal to 4x, and then you can solve for x, and you get x is equal to 1. All right, in this second example, we're looking for this value of x, which is in our exponent. So in order to solve for that, we need to take the log of both sides. Then we're going to use our inverse property to solve for x. And then lastly, we can use our change of base formula to estimate the value of x. And we can estimate the log of 72 divided by the log of 5 as approximately 2.6572. All right, again, try these next couple on your own. You can pause the video while you work and then unpause for the solution. So in this first example, the first thing you need to do is isolate that 8 to the 3x plus 2 power so that you can eliminate the base in order to solve for x. So we're going to add 6 to both sides. And we're going to take log base 8 of both sides and then use the inverse property to cancel out that log base 8 of 8. So we're left with 3x plus 2 equals log base 8 of 11. Then to simplify this log base 8 of 11, we're going to use the change of base formula. So we can approximate that as about 1.1531. And then we're going to solve for x by subtracting 2 from both sides and then divide it by 3. And we get x is approximately equal to 0.2823. So in this second example, first step is to isolate the e to the 0.5 x power. So we subtract 2 from both sides. And again, we want to isolate the e to the 0.5 x power, so we're going to divide both sides by 3. Next, we want to solve for x, so we need to eliminate that base. And we're going to do that by taking the natural log of both sides. And then lastly, we're going to use the inverse property. So we end up with 0.5x is equal to the natural log of 1. The natural log of 1, if you put it into your calculator, is 0. So 0.5x equals 0. So therefore, x is equal to 0. All right, now let's look at properties of equality for logarithmic equations. So this equality property is similar to the exponential property of equality, but here we're dealing with logarithms. So if we have log base 2 of x is equal to log base 2 of 7, then x has to be equal to 7. So let's look at this first example. We're going to solve log base 7 of 6x minus 16, and that's equal to log base 7 of x minus 1. Well, you should notice that both sides have log base 7 of something. So 6x minus 16 is equal to x minus 1. And then we're just going to solve for x. So we're going to subtract x from both sides, and we're going to add 16 to both sides. So we get 5x is equal to 15. Divide both sides by 3. And we're left with x is equal to 5. We should divide both sides by 5 in order to isolate our x. And we end up with x is equal to 3. All right, let's look at an example here where we have to put this into exponential form. So we want to put log base 5 of 3x minus 8 is equal to 2 in exponential form. So we're going to rewrite it as 5 to the second power is equal to 3x minus 8. And then we're going to solve for x this way. So 5 squared is 25. And that's equal to 3x minus 8. Then we can add 8 to both sides. And we get 32. Oh, 33. is equal to 3x. And then we can divide both sides by 3. And we're left with 11 is equal to x. All right, in this last example, we have, we're going to apply still the same properties that we've been using, but in this case, we have two separate logs where we're adding these together, and so we're going to end up with an x squared term, which is going to give us two answers. And when that happens, we always have to make sure we check for extraneous solutions. So there are two ways you could do this. The first way, you can graph this equation. So y1 is going to be log of 5x plus log of x minus 1. And then your second equation is going to be the right side, or your second y value, your equation in your graph is going to be the right side of your equation, which is just y equals 2, and then find the intersection. Using the calc function on the graphing screen of your calculator. Now the second way you can do this, because you won't always have your graphing calculator available on quizzes or tests, is to use algebra. So you want to think of your properties of logarithms. So since we're adding here, that means we're using the product property. So log of 5x plus log of x minus 1 is the same as log of 5x times x minus 1, and that's equal to 2. And then secondly, since we don't have an indicated base, we know that the base is 10, so we can write this in exponential form. So we have 10 to the second power is equal to 5x times x minus 1. So 100 is equal to 5x squared minus 5x. 5 is a factor in all of these terms, so I'm going to go ahead and divide by 5 just to make it a little bit simpler. And I have now 20 is equal to x squared minus x. Since I have a quadratic function here, I'm going to set this equal to 0 and then factor. So x squared minus x minus 20 is equal to 0. Now I'm looking for factors of negative 20 that add up to negative 1. So I have x minus 5 times x plus 4. That's equal to 0. So my x values are 5 and negative 4. Now, because I have two answers, I need to check for extraneous solutions. So you need to remember that your base and your y value, so log base b y equals x, b and y have to be greater than 0. So let's double check our solution 5 first, and we'll plug it into the original equation. So this y value, 5x, has to be greater than 0. So 5 times 5 is greater than 0. And then secondly, this has to be greater than 0. So 5 minus 1 is 4. That's greater than 0. Now let's double check for when x is negative 4. 5 times negative 4 is negative 20. That is not greater than 0. So right away, we know that this is extraneous. Which means x minus 5 is our only solution. All right, so here's a few more problems. Please try these ones on your own, and you can pause the video while you work, and then unpause for the solution. So in our first example, we have x equals 6, and that's by using the logarithmic equality property. In our second example, we're going to rewrite this into exponential form. And by doing that, we get 27, or 3 cubed, is equal to 2x plus 9. And then to solve for x, we get x is equal to 9. Now try these last two. You can pause the video while you work, and then unpause for the solution. Remember, in this one, since you have log base 6 of x minus 9 plus log base 6 of x, you want to check for extraneous solutions. All right, again for this one, we need to write this in exponential form, which is 4 to the 5th power equals this 10x plus 624. And then we're going to solve for x by subtracting 624 from both sides and then dividing by 10. So our x value is 40. So first we're going to use the product property, and we get log base 6 of x minus 9 times x is equal to 2. And we're going to rewrite that in exponential form, which gives us 36 is equal to x squared minus 9 once we simplify. Then we can factor, so x squared minus 9x minus 36 is equal to 0, factors as x minus 12 times x minus 3 is equal to 0. So now we can solve using the zero product property, and we get x is equal to 12, or x is equal to negative 3. Now the next step is we have to check for extraneous solutions since we have 2. And the way we're going to check for that is to make sure our y values are both positive. So right away we know that log base 6 of x, one of our answers is negative 3, which means that this value would be negative. And we can't have a negative number, we can't take the log of a negative number. So therefore x cannot be 3. So now let's just make sure 12 works. 12 minus 9 is positive 3, and that's greater than 0, and also 12 is greater than 0. So our only answer is x is equal to 12 because negative 3 is an extraneous solution. So please jot down any questions or notes that you have, and we can discuss them in class when I see you. Thank you.